Good morning, dear students, and welcome back to our course. In the last lecture, we had a discussion on what exactly sensitivity is and what is the use of feedback in case of closed loop control system. So, as far as feedback is concerned, basically we have two different techniques through which we can provide feedback in control system. First one is positive feedback, and second one is called as negative feedback. In case of positive feedback system, we have the open loop transfer function, closed loop transfer function for a system like g of s upon 1 minus g of s into h of s. And in case of negative feedback system, we have the transfer function like g of s upon 1 plus g of s into h of s. And then we discussed in detail about the concept of sensitivity. So what is sensitivity? It is nothing but a parameter through which we are in a position to identify that how the output of the system is going to change if some parameter of the system is going to vary. That parameter may be vary due to change in the environmental condition like internal disturbances or external disturbances, but if due to change in the environmental condition system parameter is going to vary, that is responsible to change the output of the system. So how the output of system is going to vary due to change in the parametric function or due to change in the parameter of the system, that we can identify through sensitivity. That is important. And then we discussed in detail about how to find out sensitivity in case of open loop control system, closed loop control system, and finally we conclude that in case of open loop control system, the sensitivity of overall transfer function indicated by symbol m of s with respect to forward path gain, that is nothing but g of s, is indicated by symbol s of m of g or sm of g, which is nothing but g of s upon m of s into dou m of s by dou g of s, and this is going to be 1. That means sensitivity factor of overall transfer function with respect to forward path gain in case of open loop control system is always going to be unity. They are highly sensitive. That is important. And then in case of closed loop control system, we have two possible conditions. We can identify the sensitivity of overall transfer function due to change in forward path gain, or it may possible that we can calculate the sensitivity of overall transfer function m of s with respect to change in feedback path gain, that is nothing but h of s. So equation number 8 indicate that the sensitivity of overall transfer function with respect to change in forward path gain is nothing but 1 divided by 1 plus g of s into h of s. So if you compare equation number 8 and equation number 7, it is very clear that sensitivity in case of open loop transfer function is more as compared to the sensitivity of overall transfer function due to change in forward path gain in case of closed loop transfer function. In open loop, the value is exactly 1, but in closed loop, the value is divided by a factor of 1 plus g of s into h of s. This is very important. And then if you calculate the sensitivity of overall transfer function with respect to feedback path gain in case of closed loop transfer function, this particular value is multiplied by a factor of minus g of s into h of s, or if you take the magnitude, it is multiplied by a factor of g of s into h of s. So from equation number 7, 8 and 10, or you can say 9, it is very clear that sensitivity in open loop control system is at highest possible value, which is nothing but 1. Then after that we have the sensitivity factor of closed loop control system when we are trying to find out with respect to feedback path gain. The value is minus g of s into h of s upon 1 plus g of s into h of s, and then this will be at least possible value. That means sensitivity of overall transfer function with respect to change in forward path gain in case of closed loop control system, and the value is 1 divided by 1 plus g of s into h of s. So these are very important mathematical formulae which plays an important role in order to understand and solve numerical on sensitivity. So up to this particular part we discussed in the last lecture, Today we will solve some numerical on sensitivity calculations, and then we will start next portion of our course that deals with the concept of time response analysis of a control system. As I told you that this particular portion is common for both electrical and electronics communication engineering students, those who are preparing for GATE exam. So in GATE exam, if you have a questions on sensitivity, it may be like a theoretical one where you have to solve the theoretical question based on the theory of sensitivity, or it may possible that you may have a questions like 2 mark questions on the calculations for sensitivity or numericals on sensitivity. So let us begin with our today's session. This will be the first numerical on sensitivity, and here our objective is determine the sensitivity of overall closed loop transfer function of a system shown in figure 6.8.3 at omega equals to 1 radian per second with respect to forward path transfer function and with respect to feedback path transfer function. So here what is our objective? We need to determine the sensitivity of overall closed loop transfer function, and the system is shown over here. So this is what our system is with negative feedback system. This is very important, and this indicate your forward path gain g of s having the value equals to 25 divided by s in bracket s plus 2, and this indicate feedback path gain of value h of s equals to 0.25. That is important, and our objective is to determine the sensitivity of the system at omega equals to 1 radian per second with respect to forward path function and with respect to feedback path transfer function. So sensitivity of the transfer function with respect to change in forward path gain, and we know that formula is 1 upon 1 plus g of s into h of s. That's it. In the same way, sensitivity of overall transfer function with respect to feedback path gain, we know the formula, that is minus g of s into h of s whole divided by 1 plus g of s into h of s. So it is a very simple numerical in which if you know these formulas, you can straight away put the value of g of s, h of s in these equations and then calculate the value of sensitivity at corresponding angular frequency. That's it. So I want everybody to please note down this, draw this diagram, apply a proper logic. I have also already mentioned the formulas that you need to implement in order to solve this numerical. So if you apply that logic, we know that sensitivity of overall transfer function with respect to forward path gain is nothing but 1 upon 1 plus g of s into h of s. And I told you that what is g of s? This indicates g of s. 25 divided by s into s plus 2. And what is h of s? It is 0.25. So if you get this, this will be the formula, or this will be the expression for sensitivity of closed loop system with respect to change in forward path gain. Now this is a general formula. Now we need to calculate the value of sensitivity at omega equals to, I think, 1 radian per second. So what we need to do, we need to now replace this s by omega. So we can replace this s by j omega. That's it. So if you apply that logic over here by replacing s by j omega, you will get this as an output. Now at omega, we need to replace them by 1 radian per second. That's it. If you solve this, you will get this as an output. And suppose if you're interested to calculate the magnitude, you need to take square root of, I can calculate the magnitude for this numerator. It is like square root of minus 1 square plus 2 square. It will be like square root of 1 plus 2 is 4. It will be square root of 5. In the same way, for denominator, I can calculate like square root of 5.25 square plus 2 square. That's it. And if you apply that logic, you will get the sensitivity of closed loop control system due to change in forward path gain is 0.398. So I'm writing here sensitivity of overall transfer function due to change in forward path gain is nothing but 0.398, or it is close to 0.4. Please note down this. It is simply formula based numerical. If you know the formula to calculate sensitivity of a closed loop system due to change in forward path gain, then it is very easy for you to analyze this numerical and solve this numerical. Now let us try to solve the part B or second portion of the same numerical. That means calculation for the sensitivity of overall transfer function due to change in feedback path gain. This is very important. That means h of s. So what is the formula for this? We already derived that formula. It will be minus g of s into h of s upon 1 plus g of s into h of s. Now what we need to do? Put the value of g of s, h of s in this equation. Solve it. You will get this as an output. Now again we need to calculate the sensitivity at omega equals to 1 radian per second. So for that we need to represent above equation, that means this particular equation, in terms of omega. So we need to replace s by j omega. So the moment you replace this by j omega, and if you solve this equation, you will get this as an output. And here we need to replace omega by 1 radian per second, because our objective is to calculate the sensitivity at this particular frequency. The moment you put omega equals to 1, you will get this as an output. And solve, you will get this. And then if you calculate the magnitude by applying that logic, calculating the magnitude of this complex number, it will be square root of 5.25 square plus square of 2. It will be minus 1.11. And finally, in the previous section, we got the sensitivity of overall transfer function with respect to feed forward path gain. It is nothing but 0.398. And here the sensitivity of the same system due to change in feedback path gain, if you take the magnitude, it is 1.11. So from this it is very clear that closed loop control systems are highly sensitive if we change the feedback path gain or parameter as compared to forward path gain or forward path parameter. That is important. So same thing is mentioned over here. See, if you compare equation number 1 and equation number 2, we conclude that closed loop control systems are more sensitive to change in feedback path gain as compared to the change in forward path gain. Why? Because from this it is very clear that in case of uh, closed loop control system, when we are trying to calculate its sensitivity due to change in forward path gain, the value is 0.4. But for the same system, if we try to calculate the sensitivity with respect to feedback path gain, the value is 1.11, almost 3 times. See, if you multiply by 3, you will get 1.2. So almost 3 times the system is sensitive. That is important, 3 to 4 times. So this is very important. This is the final conclusions. So it may possible that you may have a theoretical type of questions on this particular topic in gate, or it may possible that you may have numerical type questions on this particular topic. The thing is that if you know the final formulas to calculate the sensitivity of a system, in case of open loop system, in case of closed loop control system, due to change in forward path gain or due to change in feedback path gain, then it is very easy for us to solve those numerically. So take your time, write down this is the final conclusions of a numerical. So this will be the end for this particular topic. Now let us try to start the other topic of our domain that deals with the concept of time domain analysis of control system. Sorry for the disturbance. Okay, so So the next topic that we need to start in our course deals with the concept of time domain analysis of control system. So in this particular topic, our objective is to understand the analysis of a system in time domain. So first of all, let us try to understand what is the meaning of analysis, and then we will study what is the meaning of time domain analysis. So as far as analysis word is concerned, it is nothing but a process of finding the response of a system, finding the response of a system when it is excited by some input. When it is excited by some input. So that process is called as analysis. That means, suppose if you have a system having some transfer function like this, and if you apply some input to the system in the form of excitation, maybe say r of t, and you are trying to find out what will be the output of this particular system, that is nothing but c of t. That process is called as analysis. That means in case of analysis, you have a knowledge about the system in detail, that what are the parameters which are responsible for the formation of that particular system, and you are trying to identify that. Suppose if that system is excited by some input, that means you also have the knowledge about input, whether it is a step input, ramp input, parabolic input, or impulse input, what kind of input you are provided as an excitation to that particular system. So you have the knowledge about system, you have the knowledge about input, and you are trying to find out that suppose if this input is provided as an excitation to this particular system, how it is going to generate output, what will be the output, what will be the nature of that particular output. That process is called as analysis. Now suppose if that output you are going to study, or if you are going to identify the behavior of that particular output with respect to time domain, time domain, then the process is called as time domain analysis of a given system. That means in time domain analysis of a system, we are trying to identify that suppose if you have a system, and to that system if you are providing some input in the form of excitation, number one, how that particular system is going to generate the output, and number two, how that output is going to vary with respect to time. That is important. So that process is called as time domain analysis of a control system. I hope this point is clear to everyone. There is a meaning for analysis. Analysis means if you know the system, if you know what type of input you are providing as an excitation to that particular system, and if you are trying to find out the output of that particular system, then the process is called as analysis. And it may possible that the output is going to vary with respect to time. Then how that output is going to vary with respect to time, that is nothing but time domain analysis of that particular system. So if you apply this logic, we can define this as time domain analysis of control system means to study the response, or you can say output, generated by a system in time domain when it is excited by some standard test input signal. That is important. Standard test input signal. So that process is called as time domain analysis. Now, the total time response of a control systems we can classify into two main part. First one is called as transient response, and second one is called as steady state response. So transient response indicated by symbol ct of t, and steady state response is indicated by symbol css of t. And if you club this, you will get the total response of the system, which is nothing but c of t. So Ultimately, our objective is, suppose if you have a system, and to that particular system if you apply some input in the form of excitation, that input may be of any kind, it may be of any standard test input signal, and definitely it is going to generate some output in the form of response. That response is again a function of time. So how this response is going to vary, if you are trying to identify that, that means you are doing time domain analysis of that particular system. That's it. Now the response that is generated by this particular system in time domain, we can have two main parts in it. First one is called as transient response, and second one is called as steady state response. Now let us try to understand each one of them in detail. What exactly transient response in, and what exactly steady state response is. So transient response means what? It is the response generated by the system before it reaches to its final steady state value. That is important. The transient response of a control system may be exponential, or we can say overdamped or underdamped, or it may be oscillatory, again overdamped or underdamped. Normally it is denoted by symbol Ct of t, as I told you that there is a technique to represent transient response as well as steady state response. So transient response are indicated by symbol Ct of t. And these are nothing but the response generated by the system before it reaches the final steady state value. The nature of transient response may be of any kind. It may be exponential, it may be oscillatory. In exponential, again, we have two possibility: overdamped, underdamped, or sometimes it will be a critical damped also. Critical damped means what? The system is neither going to overdamped nor going to underdamped. It is going to reach its desired value without overshoot or undershoot the final value. Now, in order to achieve the final steady state value, this is very important. Huh? In order to achieve the final steady state value, a system must go through a satisfactory transient period. This is very, very important. And its period must vanishes over a specific duration of time. That means, suppose if you have a system, and suppose if you're interested to find out the stability of that particular system. So the moment you provide some input to that particular system, definitely the response start generating by that particular system. And suppose the desired output of the system is 1. When the input provided to that particular system is 0, the output is nothing but 0. The moment you provide some input to that particular system, definitely output will try to reach to its final desired value. But during this shift from 0 to 1, it has to follow some path, it has to follow some response. That response is called as transient response. And the system to reach its final steady state value, the system must go through a satisfactory transient period. That is important. And its transient period must be vanishes over a specific duration of time. Why? Because our final state must be 1. Then only we can say that the system is absolutely stable. That is important. So from this particular statement, we can also have an idea how to we can define the stability of the system. But for time being, let us consider that what is time transient response of a system. It is nothing but the time taken by the response of a system before it reaches to its final steady state value. That time is called as transient time. That's it. A system in which the value of transient period vanishes over a specific duration of time, the system is said to be a stable system. I told you that. The same thing is mentioned over here. And mathematically, we can write the expression for stable system like, as t tends to infinity, the value of transient time response system must going to be 0, or it must get vanishes. then only we can say that the system is absolutely stable. So this is very important mathematical expression through which we can identify that whether the system is stable or unstable. Now let us try to identify that what are the importance of doing transient response analysis of a system, or what are the significance of this, or what information we can get from transient response analysis. Number one, at what time the system will indicate the output after it is excited by input test signal. That means we are in a position to make a comment on system time constant. This is very important. फॉर एग्जाम्पल अगर आपको किसी पर्टिकुलर सिस्टम का टाइम कांस्टेंट फाइंड आउट करना है, तो वो आप कहाँ से फाइंड आउट कर सकते हैं? उस पर्टिकुलर सिस्टम का ट्रांजिएंट रिस्पॉन्स स्टडी करके. एंड टाइम कांस्टेंट is nothing but a crucial parameter of a system that will decide that how much time the response of the system is going to take to reach its final value. One time constant means what? It is the time taken by the response of the system to reach 63.2% of its final value. Okay. For time being, let us consider that this is nothing but the definition for time constant. In the coming session, if time permits, we will discuss why this factor is only 63.2%. Why not any other value? But for time being, let us consider that what is time constant? It is nothing but the time taken by the response of the system to reach 63.2% of its final value in first attempt. That is nothing but the time constant. So if you are interested to find out the time constant of the system, we can identify that using transient response analysis of the system. Then we are also in a position to identify the nature of response. That means whether it is going to oscillate, whether it is going to follow the exponential path in order to reach its final desired value, that we can also identify through this. And what is the rate of change of output during the entire transient period, that we can also identify through this particular process. We can also make a comment on system stability. As I told you that a system is said to be stable if limit t tends to infinity, ct of t must be equals to 0. Then we can say that the system is stable. So stability we can also find out through transient response analysis of the system. Now let us try to discuss what exactly the meaning of steady state response. It is nothing but a part of total time. Total time response means C of t. So it is a part of total time response generated by the system once the transient response is over. That means transient response खत्म होने के बाद total time response का जो भी portion बचेगा, that portion is nothing but your steady state response. So mathematically we can write here as steady state response is nothing but total response minus transient response. That's it. It is denoted by symbol CSS of t. And by knowing the steady state response of the system, we are in a position to determine the variation in the desired output and the actual output of the system. The difference between desired output and actual output is known as steady state error. This is very important. That means if you are interested to find out the expression for steady state error or the value for steady state error for a given system, we need to calculate the steady state response of the system. Because if we have a knowledge about steady state response of a system, then only it is possible for us to make a comment on the steady state error. Because steady state error is basically the difference between desired output and the actual output. And the moment we have not done steady state response, we are not in a position to find out the actual response or the actual output of the system. We know that what will be the desired output. For example, if the system is provided with some input, say x of t, corresponding to that, what will be the output it is going to generate? This will be your desired output. But how exactly this system is going to generate the output, whether it is going to generate the output like y of t, or it is going to generate the output like y1 of t or y2 of t, that we need to do or find out through steady state response. And once we have the knowledge about the actual output, we can make a difference between the desired output and the actual output. And this difference is known as steady state error. That is important. Hence, we need to do steady state response analysis of a system. So, we can also determine the performance of the system if we know the steady state error of the system. So, hence, we can write mathematically total time response of the system is nothing but C of t going to be equal to Ct of t plus Css of t. That is important. And the same thing is mentioned over here. Suppose we have a system, and to that particular system we apply some test input signal. And here, for sake of example, I have considered that the input is nothing but a step input signal. So here I have considered a system, and to that system we are trying to apply some input in the form of excitation. And this is what the input is. This is the example of your step input signal. Step input signal. Now we are trying to find out how the system is going to generate the response. Response of the system is something like this. See, initially the moment we have not applied any input, the response is nothing but zero. The moment we apply a step input, it is going to generate some response like this. It is oscillatory in nature, and finally it is going to reach to its desired value. So this is nothing but the desired value, and this will be the actual value or actual output. And the difference between desired value and actual value is nothing but steady state error. From time t equals to 0 to say time t equals to say x second, this particular range defines the transient response of the system. And the moment transient response over, the remaining portion of the total response is nothing but steady state response, CSS of t. And the addition of these two is nothing but the total response of the system, that is nothing but C of t. So if you are interested to find out the stability of a system, or if you are interested to find out the time response or time constant of the system, go for transient response study. And suppose if you are interested to find out the steady state error and the performance of the system, go for steady state response analysis of the system. So I want everyone to please draw this, because this is the overall time response of a system where we indicate transient response as well as steady state response. And we also discuss what is the importance of transient response, what informations we can get from transient response. I hope this is drawn by everyone because this indicate the general variation of overall response of the system, which consists of two main components. First one is transient response and second one will be the steady state response. Now let us try to understand the concept of standard test input signal. As I told you that in order to analyze the behavior of a system in time domain, the process is we must know in detail about the system, like its parametric function. Then we must know what type of input we are providing in the form of excitation. And basically, we have some standard test input signal through which we are in a position to identify the behavior of the system, or you can say the response of the system that is going to be generated by the system in time domain. So, in order to do the time response analysis of any system, first of all, we must know what are the different types of test input signals which are available with us, through which we have the flexibility to determine the time response analysis of the system. So, what is the meaning of this standard test input signal? So, in order to understand the time response analysis of a system, it is excited by some standard test input signal. And these standard test input signals are again classified into four main domain, or you can say basically we have four different types of standard test input signal. Now, what are they? First one is called as step input signal. Sometimes this step input signal is also called as step function or displacement function. Then second one is called as ramp input signal, also called as ramp function or velocity function. Then third one is parabolic input signal or parabolic function. Sometimes this signal is also called as acceleration function. And fourth one is called as impulse input signal. We have these standard test input signal through which we are going to identify the time response analysis of a system. The thing is that we may take any one of the input as an excitation, provide that excitation as an input to the system, and let us try to identify that how the response of the system is going to vary with respect to time. The process is called as time response analysis. Now the question is that why we have only these four standard test input signal only? Why not five or why not three? Why we have only four standard test input signal, and why we name them like test input signal or step input signal, then ramp input signal, parabolic, and impulse? Why their name is not the different one, or why we have only four test input signal and why they are like step, ramp, parabolic, and impulse? Why not five or why not three? So let us first analyze that. So same thing is mentioned over here, and you need to try to answer these questions. Why these signals are called as standard test input signal? Number one. Number two, why there are only four standard test input signal? Why not three or why not five? What is the physical significance of these input signals? And give practical examples for each one of the type of input signal. Yes, think on these questions, and if you have, you can reply in the chat box also. Yes, why these signals are called as standard test input signal? Anybody? Do you have an answer for this question? Why they are called as standard test input signal? Then Why there are only four standard test input signal? Why not three or why not five? What is the physical significance of these input signal? And give some practical examples for this. प्रैक्टिकल एग्जांपल्स क्या रहेंगे इन इनपुट सिग्नल के? फॉर एग्जांपल, अगर मैंने अभी आपको बोला कि एक स्टेप इनपुट सिग्नल का मुझे प्रैक्टिकल एग्जांपल देके बताओ, तो आर यू इन अ पोजीशन टू गिव द एग्जांपल्स फॉर दैट? Think on these questions, and if you have any answer, please reply in the chat box. Now let us try to understand the answers for these questions one by one. Why these signals are called as standard test input signal? Before that, let us consider a system. Now in this case, I have considered a system where we have a resistor of value R, and we have a switch, and we have a supply of value 20 volt. And in this particular system, our objective is we want to supply this 20 volt to this particular resistor. Okay, now let us try to identify that what are the ways different ways in which we can supply this 20 volt input to this particular load, which is nothing but the system in our case. Because if you treat this particular circuit as far as control system point of view, here this is going to be the plant, this is going to be the controller, and this is going to be the input. And our objective is we want to supply this input of value 20 volt to this particular system, and we are trying to identify that what are the different ways through which we can provide this input of value 20 volt as an excitation to this particular resistor. Think and then tell me, कितने ऐसे तरीके हैं जिसके थ्रू मैं 20 वोल्ट इनपुट मेरे रेजिस्टर को दे सकता हूं? केस नंबर वन. अब केस नंबर वन में हम क्या करेंगे? सी, एट टाइम t इक्वल्स टू 0 प्लस we will close the switch. The moment at time t equals to 0 plus, I will close this particular switch. Whatever the input which is available with us, which is nothing but 20 volt, means the entire 20 volt is going to appear across this particular resistor. I hope this point is clear to everyone. So this is the first case. See, our objective is we want to supply this 20 volt input in the form of excitation to this particular resistor of value R ohm. And now we are trying to identify that what are the different types of technique, or what are the different types of ways through which we can provide this 20 volt input to this particular resistor. And we have considered the first case in which we close the switch at t equals to 0 plus, and whatever the input which is available with us, which is nothing but 20 volt in this case, the entire 20 volt we are going to apply as an input to that particular resistor. So same thing is mentioned over here. See, in this table, at t equals to 0, let me write over here, at t equals to 0, the input applied to the resistor is nothing but 0 volt, because the switch is open. Switch is open. And the moment we close the switch at t equals to 0 plus, we have applied the entire voltage of value 20 volt across that particular resistor. Now, on this particular graph, I have indicated the input voltage that we have applied across that particular resistor. So see, at t equals to 0, the input is 0. At t equals to 0 plus, very next moment we apply the entire voltage, and this entire 20 volt is going to appear across that particular resistor continuously. The moment we close this particular switch, 20 volt is going to appear across that particular resistor, and this will remain always 20 volt, like this. So this will be the first case. Now let us try to identify the second case. In second technique, what we are going to do, at time t equals to 0 plus, we will close the switch, and now the input we are going to increase gradually and linearly. This is important. That means instead of providing this 20 volt straight away across this particular resistor, now what we are going to do, we will close the switch at t equals to 0 plus, and now through some arrangement we are linearly and gradually increasing the voltage across the resistor. For example, see over here in table, at time t equals to 0, the input applied across the resistor is 0. At time t equal to 1 second, we apply 1 volt. At time t equal to 2 second, we apply 2 volt. At time t equal to 3 second, we apply 3 volt, and so on. In this way, at time t equal to 20 second, we apply entire 20 volt. And this is what the variation of input with respect to time. See, the same thing is mentioned over here. Now in this case, instead of applying the entire 20 volt in one stroke, now we apply that voltage in a linear and gradually increasing manner, like this. This is important. So this is the another way in which we can provide this 20 volt as an input to the resistor. This will be the case 2. Remember one thing, we are trying to identify that what are the different techniques or what are the different types of ways through which we can provide this 20 volt input to this particular resistor. So in case 1, we close the switch, whatever the voltage available with us, which is nothing but 20 volt, straight away we apply that 20 volt across the resistor in one step. In case number 2, we need to provide 20 volt as an input to this particular resistor, but now we are increasing that voltage linearly and gradually. That is important. Now let us try to identify that what will be the third case or any other possibility to provide this 20 volt as an input to the resistor. Is there any other possibility? Yes, there will be a possibility, and the possibility is at time t equals to 0 plus, we will close the switch and the input is 20 volt. We need to apply this particular input as an excitation to the resistor. Now in this case, what we are going to do, we will increase the voltage but suddenly and non-linearly. This is important. In case number 2, we increase the voltage gradually and linearly. But in case number 3, we will increase the input suddenly and non-linearly. This is important. So here, by using some external mechanism, definitely we need to have that provision to change the voltage suddenly and non-linearly. See in the table, at t equals to 0, we apply no voltage. That's why voltage is 0. At t equals to 1 second, we apply 1 volt. At t equals to 2, instead of providing 2 volt, we suddenly increase the voltage to 4. At t equals to 3 second, we non-linearly increase the voltage from 4 to 9. And then for 4 we increase to 16, and finally at 5 we apply entire 20 volt as an input. So if you see the variation of input with respect to time, the graph is something like this. See, it is something like this. So this is the another way of providing this 20 volt as an input to the resistor. The thing is that at t equals to 0 plus, we close the switch and we increase the value of input voltage suddenly and non-linearly. So we will get the variation of input with respect to time like this. This will be the case number 3. Now let us again think, is there any possibility to apply this 20 volt input to this particular resistor? In case 1, we close the switch and entire 20 volt is applied in one stroke, like this. In case number 2, we increase the voltage linearly and gradually. That means 20 वोल्ट तो देना है, तो क्यों ना 20 वोल्ट को linearly और gradually बढ़ाया जाए. In case number 3, 20 वोल्ट देना है, लेकिन हम क्या करेंगे, suddenly and non linearly बढ़ाएंगे. Then what will be the case number 4? Is there any possibility to provide this 20 volt input to this particular resistor? Yes, there will be case number 4. And in this case, what we need to do, at t equals to 0, switch is closed. The entire 20 volt is applied as an input to the resistor. And the very next moment, that is t equals to 0 plus, we will open the switch. What is the meaning of this? See here, at t equals to 0, we will close the switch. The moment we close the switch, this 20 volt input is going to appear across this particular resistor. And in the very next moment, at t equals to 0 plus, we will again open the switch. That means whatever the voltage which is going to be appear across this particular resistor, which is nothing but 20 volt previously, now this is going to be 0. See here, at t equals to 0, we apply the voltage 20, and the very next moment we open the switch. So voltage across resistor is going to be 0. So the variation of input with respect to time is like this. For a very short span of time, we apply entire 20 volt across the resistor, and then we remove that particular voltage. So this is the fourth way through which we can provide this input as an excitation to this particular system, which is nothing but resistor in our case. Let us think, is there any another possibility to provide this 20 volt as an input to this particular resistor? The answer is no. That means we have only 4 different techniques to provide input to these resistors, or you can say we have only 4 different ways to provide input to any system. First one is case 1, where whatever the input which is available with us, provide entire input in one stroke to that particular system. In case number 2, we supply that system, we supply that input to the system, but in a linear and gradual manner. In step number 3, we will provide that input to the system, but in non-linear manner, sudden and non-linear. And in step number 4, or in case number 4, we will provide the input, entire input to the system, and in the very next moment we will take that input from the system. So because we have only 4 different ways to provide input to any system, that's why we have only 4 standard test input signal, because these 4 standard test input signal represent what are the different types of ways through which we can provide input to any system. Because we have 4 techniques only, 4 ways only, that's why we have 4 different types of standard test input signal. ये तरीके हैं जिसके थ्रू आप किसी भी सिस्टम को इनपुट प्रोवाइड कर सकते हैं. और कोई भी फिजिकल सिस्टम अगर आप लोगे तो आपके पास में 4 ही तरीके हैं. एक तो आपने इनपुट पूरा दे देना है, दैट इज कॉल्ड एज स्टेप. दूसरे केस में आपने इनपुट देना है बट लीनियरली उसको वैरी करके, दैट इज कॉल्ड एज रैम्प. थर्ड केस में आपने इनपुट देना है बट नॉन लीनियरिटी के साथ में, कभी आप 1 वोल्ट दे रहे हो, कभी आप 4 वोल्ट दे रहे हो, कभी आप 10 वोल्ट दे रहे हो. दैट प्रोसेस इज कॉल्ड एज प्रोवाइडिंग इनपुट to that particular system but in non-linear manner, also known as parabolic input excitation. And fourth technique है कि पूरा का पूरा इनपुट दे देना है और वेरी नेक्स्ट मोमेंट पे आपने पूरा का पूरा इनपुट वापस से ले लेना है. दैट प्रोसेस ऑफ एक्साइटिंग द सिस्टम इज कॉल्ड एज इम्पल्स इनपुट एक्साइटेशन. 4 तरीके हैं, दैट्स व्हाई वी हैव ओनली 4 स्टैंडर्ड टेस्ट इनपुट सिग्नल. I hope now this point is clear to everyone. And the same thing is now mentioned over here. First technique or case number 1, where we apply the entire input to that particular system, that is called a step input signal. And this is the way we deal with that. The mathematical function to indicate step input signal is r of t equals to r for t greater than or equals to 0, and this is going to be equals to 0 for t less than 0. That means for t less than 0, the value of input signal is going to be 0, and for t greater than or equals to 0, the value of input signal is going to be r. That's it. And suppose if you take the value of r is nothing but 1, then it is called as unit step function. And if you take the Laplace transform, it is going to be like 1 by s. This is very important. So this is called as step function, also known as displacement function. I think now it is clear to everyone, because if you take Laplace of 1, it is going to be 1 by s. The moment you take r equals to 1, it is called as unit step function. And here this 1 stand for magnitude of that particular system or signal. In the same way, we have ramp input signal. For ramp input signal, we need to increase the input gradually and linearly. That is important. The variation of input with respect to time is like this, and the slope is going to be r. Mathematically, we can define ramp input signal like this. R of t is going to be capital R into t for t greater than equals to 0, and this is going to be 0 for t less than 0. All these things you have learned in your applied mathematics. The thing is that we are just making a revision of that. And if you consider that r is going to be 1, the function is called as a unit ramp function. And if you take the Laplace transform, it is going to be like 1 by s square. This function is also called as a velocity function. That is important. And here this 1 stand for slope. That is important. So in case of unit step function, that unit stand for magnitude. In case of unit ramp function, this unit stand for slope. In the same way, we have parabolic input signal. Here the input is increases more gradually, or you can say we are trying to incorporate the non-linearity. That's it. The variation of input with respect to time is like this. Mathematically, we can represent this by these equations, like r of t is nothing but capital R into t square by 2 for t greater than equals to 0, and that is for 0, t less than 0. And if you take r equals to 1, it is called as unit ramp parabolic function. And if you take Laplace, it is going to be like 1 by s cube. That's it. Actually, uh, Laplace of t square is 2 factorial divided by s cube. Then here we have formula 1 by 2. 2 factorial is 2 into 1. This is going to be 2. This 2 will get cancelled, and you will get 1 by s cube. That's it. And this function is also called as acceleration function. Last one is impulse, where we will provide input, and very next time we are going to take the entire applied input. So in case of impulse function, the input is applied as a shock for a very short duration of time, and graphically it is something like this. And mathematically, the impulse function is given like r of t is nothing but 1 for t equals to 0, and that is 0 for t not equals to 0. That means this particular signal is going to appear for very short span of time. At t equals to 0, the signal is there, r of t is there. At t not equals to 0, the signal is going to be 0. That is the definition of impulse. And if you take the Laplace of the impulse, it is going to be 1. That's it. So finally, the Laplace of impulse is going to be 1. And in case of unit impulse function, this unit stand for area under that particular curve. See, the moment you take this as 1, that unit stand for area under this particular curve. That is important. Area under this particular curve. So in case of step, 1 stand for magnitude. In case of ramp, 1 stand for slope. And in case of impulse, 1 stand for area under the particular curve. Now the question is, in case of parabola or parabolic, this 1 stand for what? This you need to find out. So in this way, we are in a position to complete this portion of what exactly standard test input signal, why we have only four standard test input signal, why they are called as standard test input signal, because by using the combination of these four standard test input signal, we can create any kind of input signal available in the universe. That's why they are called as standard test input signal. Why we have only four standard test input signal? Because we have only four different ways to provide input to any physical system. चार ही तरीके हैं, इसलिए चार ही standard test input signal है. What is the physical significance of them and what is the practical example for them? Physical or practical example for these signals are nothing but, suppose if you have a switch, the moment you close the switch and remain closed, then that type of excitation is called as step. Suppose if you close the switch and increase the value of input voltage linearly gradually, that way of providing input is called as ramp. Suppose if you close the switch and increase the value of voltage non-linearly, that way of providing input is called as parabolic. And suppose you close the switch and the very next moment you open the switch, that way of providing input excitation is called as impulse. That is what the physical significance and the practical example of these input signal. In the next lecture, we will start and discuss in detail about the concept of steady state error. Thank you.